Hello. As you already know, ensuring high availability in distributed systems is not easy, especially in systems that prioritize autonomy, such as autonomous deployments like microservices. In this episode, you will learn a technique for deploying without downtime that will help you improve the overall situation in your system. Zero downtime deployment, also known as rolling update, is a deployment approach where there is no service interruption from the client's perspective during the process of deploying a new version. Classic deployment looks like this. We have two instances of the courses application on the server, courses 1 and courses 2. We have a load balancer that handles traffic and redirects it to both instances. If we want to upgrade from version 1 to 2, we stop both applications. At this point, they obviously stop serving client requests. We upgrade them to version 2 and restart them. When they start functioning again, they resume handling client traffic. The downside of this is that, from the client's perspective, the system was not operational during the update. Zero downtime deployments eliminate this problem. How? We have the exact same situation. Two instances of the courses application and a load balancer. The difference is that we don't upgrade both instances simultaneously, but rather perform a rolling update, which looks as follows. We stop the application on the first instance. At this point, the second instance takes over all the traffic. From the client's perspective, everything works. The client doesn't notice the unavailability of one system. We upgrade the version on the first instance. When it comes back up, it starts handling traffic again. Both applications are now running, albeit in different versions, but from the client's perspective, the system keeps functioning. We stop the second instance. The first instance takes over all the traffic. We update the second instance, and it takes over the traffic again. The beginning and end of this process are exactly the same as in classic deployment, but the middle part is different. From the client's point of view, the system was operational throughout. It seems brilliantly simple. Is it really? Let's see where the issue lies. The problem lies in the database. If these systems share the same database, ensuring consistency between different versions becomes non-trivial. Take a look at this example. Once again, we have two applications running in the first version. After upgrading the version of the first instance, we have two applications running on the same database, but in two different versions. Ensuring consistency between them can sometimes be challenging. Of course, shortly both applications will be running on the new version. However, the necessity of having applications in different versions running on the same database requires ensuring backward compatibility between these two applications. We achieve backward compatibility by using deferred changes. Why deferred changes instead of just backward compatibility? Because it is not possible to continuously develop a system while maintaining 100% backward compatibility. Sooner or later, usually sooner, we reach a point where we need to make a breaking change. Deferred changes, spread over time, involve breaking changes being split into multiple changes, each of which is backward compatible. It may sound enigmatic, so let's see how it looks in an example. We need to make a change that involves expanding the resolution of the field from user login date to date with time. Let's temporarily name this column date and migrate it to the data time column. The first step, of course, is to add this column, but I can't immediately migrate the column. I can't simply perform an alter type column and change the column's type. That's something I could do in a classic deployment. Stop both applications, migrate the columns in the database, and start the applications now handling the new column. If I want the user not to notice this change, my applications need to handle both columns simultaneously. So, I start by adding this column and deploying version 2, which still reads data from the old column, date, and writes it to both the new and old columns. Now, why am I reading from the old column? To ensure backward compatibility with version 1, which still handles the date column. After deploying version 2 on both the first and second instances, all new changes are directed to the data time column. Now I can migrate all the pending data in the database by moving it from the date column to the data time column. Once this migration is complete, I know for certain that both the data time and date columns are up to date. Both are consistent. So, I can deploy the next version 3 of my application, which reads data from the data time column, because, as we know, it is up to date, and writes to the data time column, but also temporarily writes to the date column. Here you might wonder, why write to the date column? After all, data time is already up to date. Well, when we deploy version 3 on the first instance, remember that the second instance still runs the previous version, version 2, which still reads from the date column. If we stopped writing to the date column, it would introduce inconsistency at this point. Only when we deploy version 3 on both instances can we deploy version 4, which no longer writes to the date column, and then we can remove the date column. Removing the date column is a challenging task, just like adding the data time column. Adding a column to a running system is not trivial, especially in relational databases, as it often requires acquiring a global lock on the table, causing all write/read operations to halt. The system effectively becomes unavailable. Therefore, we need to learn about mechanisms like appropriate lock modes, which provide us with online operation. The same applies to removing the date column. Firstly, removing the date column will prevent us from reverting to version 3. That version won't work because we no longer have support for the date column. Secondly, if it turns out that I made a mistake somewhere, it will be more difficult to revert. Another issue is the activation of database compaction, which can impact the performance of our system. Let's visualize this in a more readable diagram. We have versions, we have reads, and we have writes. Version 1. Read, write from the date column. Version 2. Read from date, but we start writing to the data time column as well. Version 3. We can read from the data time column. We continue to write to both date and data time to maintain backward compatibility. Note that version 2 is compatible with version 1, version 3 is compatible with version 2, version 4 is compatible with version 3 and consistent with that version, but version 4 is no longer compatible with version 2. Version 3 is not compatible with version 1. Of course, version 4 is not compatible with version 1 either. We made a breaking change that is not backward compatible, but each stage of introducing this change, backward compatibility was maintained. What conclusions can we draw from this approach? Firstly, the change we implemented is the simplest example of a backward incompatible change. Secondly, more complex changes, such as schema denormalization or removal of a junction table, are extremely challenging to carry out in this model. For such changes, a classical deployment is required, which means introducing unavailability in a deployment window for our system. Furthermore, the mechanism you have seen here is universal, and in the coming weeks, we will apply it, for example, to meaningful versioning of a RESTful API, contract verification, and more. Thank you.